Welcome to week 4. This week has 10 sections in the reader and a lot of important ideas. So I'm dividing the overview up into 3 pieces. What we're going to do now is an overview of sections 1 to 6. There'll be another overview, shorter, for sections 7 and 8, and a third one for sections 9 and 10. But there are a lot of important ideas as we work through week 4. We're going to be working with sampling distributions, which really are the last piece of our foundation. So far, we've looked at problems where the facts about the population, including all the important things we need to do calculations, were given. So in week 2, we were given probabilities of outcomes and events. For the binomial problems, we were given the sample size and the population proportion p. Week 3, for normal curve problems, we were given the mean mu and the standard deviation sigma. Now, of course, in real-life applications, we need to estimate these parameters from samples, and we need to use our sample estimates to draw conclusions about the population and make recommendations. But the foundation for all of this, in theory, are sampling distributions. For inference problems coming up in weeks 5, 6, and 7 especially, we're going to use the sample average x bar to estimate the population mean mu, and we're going to use the sample standard deviation s to estimate the population standard deviation sigma. Most of our questions will actually be about means, but we're going to need to use the standard deviation to work with those. We'll use the sample proportion p hat to estimate the population proportion p. And a constant framework for the work we are doing is we need to work with the sampling distributions of x bar and p hat, keeping in mind that any sample we take for our study is just one of a very large number of possible samples. So here's an illustration of what this might look like. This is what the statistical theory works with: the distribution of the averages from all possible samples. And here's an illustration from Baldi and Moore. This is in chapter 13 on page 316. It looks a little bit like a cartoon, but actually it's a very clever way to illustrate one of the foundational pieces for this week. So Baldi and Moore in this picture say we've got a population, and we'll assume for a minute that we know the population mean mu is 25. We're going to take fairly small simple random samples of size 10. The first one has an x bar 26.42. The second one has an x bar 24.28. The third one has an x bar of 25.22. So what we're looking at when we do our theory is the population of x bar values. We take lots of samples, and for every sample we just write down one key feature, the value of x bar, and then we kind of put them all together in a histogram, and we ask 3 very important questions. What's the mean if we look at this distribution of x bar values? What's the variance? And what's the shape? So those are going to be the kinds of questions that we're going to work with all throughout the week 4 materials. So we have to keep saying over and over, every sample gives a different average. So here again is a little bit of that illustration from Baldi and Moore, where the first 3 samples give different averages. And the way the statistical theory works is it considers the distribution of the averages from all possible samples. So quite frankly, a lot of week 4 is like a construction site tour. We're going to have algebra in several sections to derive formulas for means and variance for sums and averages, counts, and proportions. So it's time for hard hats. Baldy and Moore just state the results, but you signed up for Berkeley MPH and Berkeley Biostat. We want to show you how it works, and quite frankly, a big goal of mine for taking you through the material in week 4 is to help you use it wisely. So here's somebody else heading out for this construction site tour. We're going to do it with lots of narrated PowerPoints, sort of like a chalk talk lecture. There's a lot of animations to try to do that. The derivations are in the week 4 reader. If you are okay with that, it's fine. You might find the narrated versions a little easier to follow. And again, really, a lot of week 4 is background to take the mystery out of the key results we're going to be using. So section 2 is going to take a look at algebraic derivation that supports some intuitive reasoning. If the average temper of a sample of flu patients is 102 degrees Fahrenheit, then the average for their temperature in degrees C or degrees Celsius is going to have to be 32.9. It's equivalent information, right? How could it be anything else, really? Well, just because it seems reasonable, mathematicians still need to verify it. And I apologize for getting a little too clever with the animation, but here's the conclusion. We're going to show in section 2 that this insight, that we just have to convert 102 degrees Fahrenheit to 38.9 degrees C, is exactly how things work. Now, this is in fact degrees Fahrenheit to degrees C, a linear transformation. We've already done some linear transformations. Z-scores are going to fit under this topic of linear transformations of random variables. Subtracting off a constant mean mu and dividing by another constant sigma. And we're going to see in week 4 that averages are just linear transformations of a sum where we multiply by a constant 1 over n or divide by it. Proportions, in the same way, are linear transformations of a count. They're just working with a known constant. So we need to do a little bit in section 2 to get everything in line for what happens with linear transformations of random variables. Section 3 is going to go through a very small example, the sum of two random variables from first principles. We're going to take a look at the average of a sum of two random variables, x and y, and we're going to see that the average of the sum is the sum of the averages. And again, this seems reasonable, but there is something to prove here. Mostly we're going to go through and work things out. We're going to derive the probability distribution of the sum S. We're going to work out the probabilities for each possible value of the sum, find the expected value. We're going to do that as an illustration rather than trying to do a general proof. Section 4 is going to talk about means and variances for sums, not just little sums of x plus y, but whole bunches of them. And we're going to have a framework for working with totals and averages for measurements from a simple random sample. So we're going to take a measurement for a subject, whether that's weighing them, taking their blood pressure, getting a lab to determine their HDL cholesterol. We're going to think of any one of these measurements on a subject as a realization of a random variable that we'll denote in general by a capital X sub I. Everybody in the sample gets their own random variable, but then we're going to turn around and say that for a homogeneous population, all these random variables have the same mean and variance. Now, this really does sound kind of Alice in Wonderland, but I hope, if you're patient, the background will start to make sense. So we're going to see that for simple random samples of size n from a homogeneous population with the mean mu and a variance sigma squared, the mean of the sum is n times mu. And in the special case of independent observations, which we're going to have in a simple random sample, the variance of the sum is n times sigma squared. And often, as is the case, when we work with these kind of examples, results for the mean can seem pretty intuitive. The results for the variance, not so much. They take a bit of algebra. So we'll do a very small kind of example for a mean and variance of a total or a sum. We'll consider calculating fuel needed for an airplane that's going to have 25 passengers and crew. We're going to assume that the 25 people are a random sample from a population whose weights have a distribution pretty close to a normal curve, with a mean weight of 190 and a standard deviation of 35 for each person. So the total weight is kind of a derived random variable off of this, and the mean is just going to be n times 190. 25 times 190 is 4750. The standard deviation is going to be the square root of 25 times 35, because the variance is n sigma squared. 5 times 35, or 175 pounds. And we'll go through and do more details where these results are coming from and how to use them for this problem. So we're also going to think about means and variances for averages of random variables. And again, we're going to think about all the values of x bar from all possible samples of a given size n. It's going to turn out, although it's going to take us a little algebra, that the average of the x bar values is the population mean mu, and the variance of the x bar is related to the population variance sigma squared. The variance of the x bars is going to be sigma squared over n. And if you take a look at this formula, one important consequence that we're going to be using throughout this course is that for larger sample sizes n, the sample x bar values are going to cluster more tightly around the mean. And that's because of that sample size n in the denominator. Here's an illustration from the reader where I've deliberately had Stata plot things on the same horizontal axis. The top graph is a histogram for averages for 10,000 samples of size 100. And the lower graph, lined up right underneath it, is the averages for 10,000 samples of size 400. And you can see that in the lower graph, the averages for the 10,000 samples of size 400 are a lot more concentrated around 66 than for samples of size 100. And we're going to do the algebra to show you where this formula comes from. Now, section 6 is going to be a little bit wild and crazy. We are going to look at counts and proportions for binomial random variables and their means and variances. But thanks to one of the famous Bernoulli family of physicists and mathematicians and probability theorists, we're going to set up counts and proportions as sums and averages of 0, 1 variables. So we're going to define these Bernoulli random variables to be a 1 for a yes or a success with probability p, and a 0 for a no or a failure with probability 1 minus p. And we'll go through the algebra to show that the mean of these random variables, all of them, is going to be p, and the variance is going to be p times 1 minus p. And once we set up these Bernoullis, the number of yes is a sum, and the proportion of yes is an average. So the mean number of yes is going to be n times p. The variance of the number of yes is going to be n times p, 1 minus p. And we'll actually not just state those the way Baldi and Moore do, we'll show you the derivation. When we work with proportions, which are a linear transformation of the sum, the mean of the proportions p hat from all possible samples is going to be the population proportion p. The variance of the proportion p hat values is going to be p times 1 minus p over n. And these are facts we're going to be using a lot. So here's a little bit of advice about what to focus on in the first 6 sections of week 4. Try to follow the derivations. You can try the narrated PowerPoints to do that. It might be helpful. We're going to use a lot of these results in weeks 5, 6, and 7. And we need to fix this because there's not a midterm anymore. It's going to be helpful for the problem set still, and when we get to the take-home final, to make your own summary. And I'm sorry I didn't catch that because I didn't mean to scare you. There is no midterm. Try to put together as we go all the formulas for means and variances, for sums and averages of continuous random variables, for counts and proportions of binomial random variables. There's also an important distinction to sort out when you take a look at the material for continuous things. You need to distinguish the population of the x values themselves, the original people's measurements, which have a mean mu and a variance sigma squared, and the mean and variance of this new theoretical population of x bar values. Mean mu, but variance sigma squared over the sample size n. Now, my hunch is that the fact that mu is the mean for both the x values themselves and the x bar values is why this is kind of potentially confusing. But you want to be on the alert now for whether we're talking about a population of x values or a population of x bar values. Sections 7 to 10 are going to have some more applied problems after we work out all the theory. And of course, they used to be called modules. Now they're called weeks. It's the same thing. So we're going to get to the applied problems at the end. The only catch with what we're doing in the last part of week 4 is that we're going to continue to assume that we know the population parameters, the mu and the sigma squared for sums and averages, the p for counts and proportions. And then here's a little more roadmap of what's coming up. Part 2 of the overview is going to be for sections 7 and 8. Part 3 of the overview is going to be for sections 9 and 10. There aren't any software videos in week 4 because there aren't any new software tools. We're still going to be using both the binomial functions in Stata and our normal distribution tools, Surfstat and Stata. So I hope this helps as you get started on the material for week 4, and try the narrated PowerPoints if reading the reader seems a little bit